This is Mrs. O'Neill for AP Chemistry, Chapter 9, Section 6, Multiple Bonds. What's so special about multiple bonds? Well, we need to identify the atomic orbitals that contribute to covalent bonding in which overlap can occur between multiple bonds. So because of this overlap, we call them sigma and pi bonds between those atoms. So we're going to classify single bonds as sigma and multiple, or your double and triple bonds as one sigma and one or more pi bonds. Okay, so we're going to examine this geometric arrangement of these bonds, and again, a lot of this has to do with organic compounds. So pause the video, fill in those blanks, and then play to hear my words. So a sigma bond is an internuclear axis that goes through the overlap area. So in other words, when bonds come together, there's either going to be an overlap area or a non-overlap area, and that's where the sigma and pi comes into play. So sigma bonds are the overlap area, where the pi bonds are the not overlap area. And remember when we did those model kits in organic chemistry way back in chapter 24, the first chapter we did, we can't rotate them, right? Those bonds don't rotate. So what happens is if we have these two pi bonds, right, they're going to come together, they're going to form a bond. However, look, there's no overlap in this area where those two p bonds come together. So the sigma is the overlapped area and the pi is the not overlapped area. So I believe in your packet of notes you have a place to put some drawings. So what do I want you to draw? Well, if you have two s orbitals coming together, right? So you have two circles, and here's your two nuclear, right? Nuclear, internuclear. Yeah, there it is. This is that internuclear axis that bonds the two nucleus, right? How they come together. So we're not talking about the size of just one atom. We're talking about the size or the overlap area of the two atoms that come together. So if we have two S's coming together, it's called a sigma bond because there's an overlapped area. Okay, so that's what you should be drawing. You should be drawing those two circles, maybe somehow drawing the area where they overlap, and that bond that forms between them, between the two nuclei, is that sigma bond because it's that overlapped area. So now, again, just to show you, we have a 1s orbital from two different atoms coming together, and again, that overlapped region is going to be that sigma bond. So how about if we have an s and a p orbital? Well, again, this is going to be considered a sigma bond because there's an overlapped area. Now, it's kind of hard to tell. It depends on how close, right? Now it's going to depend on how big those atoms are, of how much area is overlapped. So it could be something as like maybe a quarter of this p orbital. It could be half of the p orbital, or it could be almost the whole p orbital, or I should say this section of the p orbital. So it really doesn't matter how much overlaps. We just know that when an S and a P come together and it's in this orientation, it's going to have an overlapped area, and that overlapped area is considered a sigma bond area. So how about when two P's come together? Again, you have a P here, right? That's a dumbbell, and you have a P here. That's a dumbbell. Well, the dumbbell that they share in between, the overlap area, and again, that overlapped area is going to depend on what atoms are coming together. If you have two of the same, the overlap is probably going to be 50-50. But if you have a huge atom and a very small atom, of course, then it's going to be a little bit closer together. So again, though, it's where that overlap occurs between those two P orbitals that again are coming together to make a bond is going to be labeled as a sigma bond. So again, these are just all three of them showing you how two s orbitals coming together, an s and a p coming together, and two p's coming together. Again, these are all sigma bonds because of that overlap of those two orbitals coming together. So again, P can, however, be in three different orientations, right? So it can have that dumbbell or infinity shape. It could have that dumbbell or infinity shape going up and down, or it could be on that Z axis, right, where it's like on a diagonal. So because of that, when two P's coming together and they're in this orientation, well, that orientation, there is no overlap. Aha! So like in a double or a triple bond, the different P orbitals are now going to bond together, but when they bond together, there's going to be an area of no overlap. So again, we want to know that this pi area, the pi bond, is the non-overlap area. So somehow or another, you need to draw that and make sure you're understanding where that occurs. So the easiest thing to know, though, this is the easiest thing, right? So if they give you a structure and they're giving you all of these single, double, and triple bonds, and they want to know how many sigma bonds there are and how many pi bonds there are, well, for every single bond, those are all sigma bonds. Single bonds, sigma bonds. And that's why I made the S's in different colors there, right? So every single bond is going to be a sigma bond. However, when we have a double and triple, we're just going to add a pi. So a double bond is going to be one sigma. It's got to have at least one sigma, one area of overlap, and one pi bond, one area of non-overlap. And when you have a triple bond, you have one sigma bond and two pi bonds. So again, one area of overlap and two areas of non-overlap. And I'm going to show you some pictures so you kind of understand, again, it's really based off of that p orbital and being on that x, y, and z axis. So again, examples of a single bond, right? This has to be an overlapped area, so that's going to be a sigma bond. Again, overlapped area, single bonds, sigma bonds. Single, sigma. Now examples of some double bonds. Again, so we have a bond here, but that double bond, because of that P, is going to have a non-overlapped area. So you have an overlapped area and you have non-overlapped area. So now you have a sigma and a pi bond, okay? Now they're not counting each one, right? They're just counting that that's that area. Remember, because we can rotate, well, a double bond you can't rotate, but it's that area. So they're just saying that that area of non-overlapped is going to be a pi bond. So overlapped area, non-overlapped area. So a double bond will always have one sigma and one pi. So again, just to give you an idea of all of these different pictures that you can see either in your book, online, YouTube, you'll see it in your college textbooks, all of those things. Now a double bond, however, again, now your P is in a different orientation, so now there is no overlap. So that's where those pi bonds come in. So again, we have a sigma bond and we have pi bonds. Now how about triple bond? Well, a triple bond, now you have that p orbital on the z axis. So you have the single bond here, I should say, yeah, the one bond here, I should say, where there's an overlap, that's the sigma, and then you have your two areas or your two p's of non-overlapped areas, and those are going to be the two pi bonds. So a triple bond is going to be one sigma and two pi. Okay, so again, area of overlap and areas of non-overlap. So again, just to show you just different pictures, because for you visual learners, hopefully that clicks in. So again, a triple bond would be a one sigma bond and two pi bonds. Again, just to give you more examples of what's going on here, this also even shows you the hybridization, shows you the sigma and pi bonds, just to give you some of those visualizations. Now, localized versus delocalized. I bring this to your attention because localized is just electrons between two atoms. However, delocalized, that's kind of like what we call resonance structure, right? So benzene ring is a really, really good example of electrons that are delocalized, because technically, are the electrons single, double, single, or is it double, single, double, right? So those electrons, and that's why a lot of times benzene is written out this way with just a circle inside, because those electrons really are delocalized. They're not in any one specific spot. Those electrons kind of move around. So we really don't know where the double and single bonds are at any one given moment. Remember, those electrons are constantly moving. So localized are just between two, a single bond basically, because they can't really go anywhere else. They're kind of there, but when you have double bonds, then you have some delocalization going on. So again, that benzene ring, we have resonance structure, and that's why a lot of times there's just a circle in the middle. Again, just to give you some more visualizations, some nice 3D modeling here as to why those electrons can be all over the place. And it also, again, talks about hybridization, sigma and pi bonds. Again, just different views. And last but not least, again, what's going on with your sigma and your pi bonds, and talking about localized versus delocalized bonding areas. So, see you in class.